So finally we're reaching the point where electrical circuits begin to get a little bit, just a tiny teeny little bit difficult. And what we're going to look at is something called internal resistance. So I just want to review a couple of things to make sure that we've got a couple of definitions straight in our head. So first thing we're going to talk about is EMF, and be very clear what I mean when I say internal resistance. So EMF, I hope you remember, it stands for electromagnetic force, and it's the energy per unit charge that we get from the power supply. So it's transferred to electrical energy. Now, when I have a power supply, I can look at the EMF it's got, the energy or the work done per unit charge. But I can also imagine that inside my power supply, as well as giving me energy, it also takes some energy to get through the power supply. It's kind of like there's a little internal resistor inside there. And when you see this thing where I put the dot to the dot here, this is saying this is what's inside my power supply. There's something that gives me EMF, but there's also a resistor that's going to use up some energy. And that's the internal resistance. And we'll always give the internal resistance the symbol of a lowercase r. And sometimes referred to as source resistance. And it's the loss of potential difference per unit of current in the source when current passes through the source. So basically what we're saying is that if I put a power supply into a circuit, I never actually see all the energy that that power supply is providing, because some of it gets used up inside the power supply, which is why you might sometimes come across the term lost volts, because some of the volts are lost inside the power supply. Even though you may come across that term, please do not use it as an answer in the exam, because it is not technically correct. I mean, we've not lost anything. That kind of is a bit of an anathema, because we know that we have conservation of energy going on. So if I talk about having lost volts, then I'm talking about losing energy, and it's all a bit nasty. So if you come across that term, please just remember it's an analogy, it's a way of talking about it. It is not something to write down in the exam. Okay? So let's just have a little look at what's going on if I have a complete circuit, and think about everything that's involved. So here I've got my circuit. So this is the start and the end of my power supply. So we're just showing that I've got some internal resistance, and I've just got real simple, I've just got a single resistor hooked up to it. So we know from Kirchhoff's second that the total EMF in the total circuit is equal to the total PDs. So some of the EMFs is some of the PDs. So if I look at the case I've got going on opposite, my EMF is the EMF from the power supply, which is just going to be given with the symbol of our epsilon. And my potential differences come from my external load, my external resistor, plus the voltage from going through my internal resistor. So I've got IR to show the voltage from my external resistor, and an I with a little r to show the voltage from my internal resistor. You can also write it with the I pulled out separately, and you might also see it written with the V for the terminal potential difference. So I can take this idea of that my external load, the current through that multiplied by the resistance, is my external potential difference. It's how much I see out of it, so we can call it my voltage. So I can get that my EMF equals V plus IR. So the amount I put in is equal to the amount I see inside the circuit, plus however much energy I used just getting through the power supply. This gives us the more complete explanation of what's going on in the circuit. Now, when it comes to exam questions, you ignore internal resistance unless they tell you not to. So there will be specific questions where you care about internal resistance, but if they don't mention it, don't worry about it. It will be small enough to be negligible, and they will have only told you about the terminal potential difference, what we see when we get to the outside of the circuit. Okay, so just watch for that, because sometimes people overthink it and get themselves into a tizzy. So obviously you can rewrite it. I've just forgotten that I put that one in there, but I'm sure we all figured out that the terminal potential difference is the EMF minus however much energy we used up going through that internal power supply. So I mentioned the idea of lost volts, so just to show you what you mean by this. The current times the internal resistance is the amount of voltage that I use getting through the power supply. So it's the volts that never make it out. As we just said, it's the difference between the EMF and the terminal potential difference. So you could consider your EMF to be equal to your terminal potential difference plus your lost volts. And this is showing that it's the conservation of energy. Showing it like this is okay. I would much prefer you use these symbols here or this up here. But again, this is just showing, it's kind of like Kirchhoff's second, we are just showing that all the energy that goes into my circuit is coming out of my circuit. The exam board are just not keen on the use of the word lost, for reasons I'm sure you can imagine. So yeah, basically, what I get out is what I put in, minus what I waste. Kind of like life, really. Okay? Right then, so we need to know how to measure internal resistance. It is a practical, it's one of the key practicals. We are going to do it a couple of times, and you also need to be able to talk about how to do it. So basically, you set up a circuit that looks a bit like this. So I've got, this is my power supply. I'm going to put my voltmeter across the terminals of my power supply. I'll then have a current. Obviously, I'll have an ammeter to measure my current, which is going to go through a variable power supply, which could also be a resistance substitution box. We'll have a look at some of those so you know what I mean in a second. We then also have some component links back to my power supply. So it's a really simple circuit to set up. You set it up, you measure the terminal potential difference, and you measure the current. Then you vary the reading on the variable resistor, so vary the resistance, so you get more values of V and I. And the reason the bulb in there is for safety, because it's going to make sure the current doesn't get too high. But if you use large resistors, you're fine. But if you want to make a comment on safety, make sure you say you're putting a bulb in there. Keep you safe. We then plot a graph of V against I, which should look something like this. So we should find that we get a negative gradient, and we should have a non-zero intercept. So if you measure the gradient, that will be equal to minus R. So it's the negative of the internal resistance, and the EMF of the power supply is your y-intercept. So this is quite a nice one for the exam board, because they can make you get something from both the intercept and the gradient. So it is very much worth knowing that you have this in your head. So just to show you where it comes from, terminal PD is V equals IR, so my EMF equals IR plus I times the internal resistance. Rearrange that to replace my V in there, and then make sure that I rearrange for Y equals MX plus C, because I've got V on my Y, got current on my I. You should hopefully be able to see that that goes straight to Y equals MX plus C, M is minus the internal resistance, and the intercept is the EMF. Easy peasy. We should be very used to these, they should be nothing at all. So, some real life applications. Why do we care about internal resistance? Because we do. Sometimes we try and make sure it's a certain size. So, for example, car batteries, they have an EMF of about 12 volts. It doesn't sound like a lot, but it's important. It's there to make a current of about 100 amps for just a couple of seconds to spark the motor to make it turn over. In order for terminal PD not to fall significantly, so in order for that PD to stay at 12 volts, I need the power supply to have a essentially negligible internal resistance, so something in the realm of 0.01 ohms. So if I had 0.01 ohms as my internal resistance, that means I'd still lose 1 volt, but I would still have an external power supply of 11 volts. So I have to consider this, because if I don't have that potential difference, my starter motor will not turn over. So you have to consider this when you are planning things. Another example is if I have a high power energy supply, so it's sometimes called an EHT or something like that. These are the ones that will give you big high voltages, the ones that I will never let you play with. Who knows what Liam would do, but they are the ones that essentially are dangerous. And to make sure that they're not too dangerous, they have a large internal resistance, because that means that the current is limited, and it's the current that actually does damage, because it causes heating, which is what kills you basically. So it means that you can never get up to the fatal amount of, huge astronomical number here, 50 milliamps. You get a current of 50 milliamps through you, that's enough to kill you. So with the large resistance in the power supply built in to the internal resistance, it's going to keep you safe. So for an example, if we have a power supply of 3 kilovolts, it would have an internal resistance of 10 mega ohms. So that means that the biggest current, when you have a near zero load resistance, so for instance, you touch both terminals with a wet hand, because being wet reduces your resistance, that would mean that the maximum current that could flow would be 3 kilovolts over 10 mega ohms, which gives you 0.3 milliamps. That will keep you safe. It will hurt, but it will keep you safe. So again, a choice of the internal resistance has a real-world application. And one more that you may actually care about as well is about getting the maximum power out of your power supply. So the amount of power you get out will vary depending on your internal resistance, because obviously it changes your current and it changes the ratio of voltage you get on your load supply. And it varies sort of like this, with a peak and then it drops down. And the peak happens to be when your external load matches your internal resistance. So if I want to get the maximum power out of a power supply, I need to know its internal resistance so I can match the external load to it. And a real world example of this is speakers. If I want to get the loudest sound out of speakers, I want to make sure that they are hooked up to a power supply which has an internal resistance comparable to the resistance of the speakers. And there's our real world application. Maximum power is something that you can be asked to do a practical on, and or explain a practical of, and that you would need to think about how you would carry it out, what the graph would look like, and how you would read off the internal resistance using that graph. Okay, so that is it. That is the total of internal resistance. Not too bad, I hope. Just a few things to keep your mind on, and it's really the practical bit that you need to bear in mind. So make sure that you can explain how to do that practical and you know what that graph is telling you.